Look at your study guide. There are two problems on your study guide for part 3, and one of those would involve the two compound interest formulas. Now, I'll give you the formulas. You need to know how to use them. So, in number 1, you're told that you're investing $15,000 in an account that earns interest at a rate of 3.5% for 4 3/4 years.
Really quick, you said that was 4.2 part 3. Is that really 4.1 part 3?
Yeah, 4.1. Thank you. 4.1 part 3. So round to nearest cent, and then determine how much money will be in the account if, and then you have those 3 situations. Okay, so there are 2 formulas. Remember, your formulas are A equals P times 1 plus R divided by N raised to the NT. That's one of them. And you're going to use this if your interest is compounded finitely. So your interest is compounded a finite number of times. Okay? And the other one is this, A equals P times e to the RT. And when you use this one, when the interest is what? It must say what words? Continuously, yeah. All right. So this one is compounded a finite number of times. So hence the letter N. What does N stand for? Do you remember? The interest is compounded per year. So if it tells you that the interest is compounded quarterly, then what's N? 4. So that's every 3 months. If it's compounded monthly, N is 12. If it's compounded semi-annually, N is 2. Okay, so every 6 months. All right. And P is the principal. That's the original amount. T is your time, and time must be in what measure? What units? In years. It must be in years, right? Okay. And then R is your interest rate. It's got to be in decimal form. And A is the amount in the account after so many years. So in number 1, where you have part A, 1A, which of those formulas am I going to use? It says interest is compounded quarterly. Which one? The first one. All right, so we need to use the first one. So N in this case is going to be what? 4. So quarterly. So you're going to get A equals P. Remember, P stands for what word? The principal, the original amount. And what was the original amount? 15,000 times 1 plus the rate. Now the rate they have here is 3.5%, but you have to write that as a decimal. How do you write that as a decimal? Move it 2 places to the left, so that becomes 0.035. So 0.035 divided by N. What's N? 4, right? Raised to the, I'm going to put the exponent in parentheses. And so N is 4. So I'm going to say 4 times time, which is in this case 4 3/4. All right, but as a decimal, what's this? 4.75. All right, so 4 times 4.75. All right, and then just a matter of you putting that into your calculator. Now, I did say round to nearest cent. So nearest cent means like 0.35, 0.47, things like that. So in your calculator, you just type it in as you see it. So you're going to say 15,000 times, in parentheses, 1 plus, let's see, the rate is 0.035, right? Divided by 4. Close the parentheses, and then what do? Raise it, so that caret symbol right here looks like a root. It's called caret, C-A-R-E-T. I think it's an E-T. Raised to the, and then what do I put there? No, if you say 4 times 4.75 without it being in parentheses, what it's going to do is going to raise this only to the 4th power and then multiply the whole thing by 4.75, which is not what this is. Okay? So remember, if you don't put that in parentheses, what it's going to do is take what you just put in, raise it to that 4th power, and then multiply the whole thing by that. And that's not what we're doing here. All right, so we need parentheses. So parentheses 4 times 4.75, close the parentheses, press equal, and 17,000 to the nearest cent. What would that be to the nearest cent? 2 decimal places, round off, 0.22. So $17,700.22. Okay? There's that was part A. 4.75, that's times. What, you mean this right here? That's multiplication symbol. You can't see, that's just a times. The symbol for multiplication, 4 times. Okay? Remember, we just approximated. Remember, that's an approximation, right? Okay. Now, if you put equal sign, that's no big deal, but it is an approximation. Okay, and then B, N in this case is what? 12. So you're going to say A equals 15,000. So all the information will be the same except for what? The N. So everything else stays the same. So you get 3.5% divided by 12. Raised to the, in parentheses, 12 times 4.75. Use your calculator. Tell me what you get. Real quickly. No, it can't be 14,000. It's got to be more, right? Okay, do you understand? Who said 14,000? Okay, yeah, but you can always determine if what you have makes any sense because it's earning interest, correct? So the amount you end up with better be more than what you started out with. Okay, so it's got to be more than 15,000. Okay. I don't know, I'm working on. All right, so you should get $17,708.74. That's what you're supposed to end up with. 74, not 73. 74. Okay, you got to round up to the nearest cent. So make sure you know how to use your calculator with this. Okay, look real closely. 15,000. 15,000 parentheses 1 plus 0.035 divided by 12. Close the parentheses. Raise it to the open parentheses. 12 times 4.75. Close, press equal. Okay? All right. If you still get it, someone on the side of you can probably show you got the same calculator. Okay? But you got to make sure you can put that in your calculator. Ask someone on the side of you. Is it the same calculator I asked you to buy? Then it's easy to put in. Ask someone on the side of you. Ask someone on the side of you, see what you're doing wrong. All right, C. Now, for C, am I going to use the letter N? No, because it's being compounded continuously. So since it's being compounded continuously, I have to use the second one. So I have to use A equals P times E to RT. So continuously is the the natural base. And what letter stands for the natural base? We used the word natural base last time. The E. So E is your natural base. So whenever it's compounded continuously, that's E. So there's no N involved because it continuously means an infinite number of times. And so all you do is just plug in what you know. So A equals P. What's P? Times E in parentheses. What's R? 0.035 times T, which is 4.75. All right, and then you put in your calculator. All right, so now here's how you're going to do this. So you're going to say 15,000. That's 15,000. So 15,000. All right, now I've got to get the function E. So how do I get to the E? Second, okay, and then that ln bun, right? So we're going to talk about natural log today. So you get that, right? Now what do I put inside the parentheses? 0.035 times 4.75, close, press equal, and you get this. All right, so $17,713, and what's the nearest cent? 2 cents. Okay. All right, so make sure you can use your calculator. Now notice that the rate's the same, the initial amount's the same, but notice the amounts are increasing. The amounts are increasing, why? Not because of the interest is the same. Why is it increasing? The number of times being compounded. So this was only 4, this is 12. So remember, interest is earning interest here 4 times. Interest is earning interest here how many times? 12. Here it's a finite number of times. Now it's not that much. See, the continuously gives you the most money, and that's what most banks probably use is the continuous one. But it's not that much, right? But it's still a larger amount. Okay, number 2. Okay, so you purchase a new car for $18,000, and the value of the car after T years is given by this function, where T is the number of years after the purchase, and V of T is the value of the car in dollars. All right. Now, you remember when we did this right here, we said that 15,000, don't use the word principal. I want you to use another word that we use. 15,000 was the what? No, not A. Initial amount. Good. That's what I want you to say. The original amount, the initial amount. Okay? So if you look at this right here, what was the initial amount? 18,000. What do you see here? 18,000. So that number right here should always be the initial amount. Okay? All right. Now this card depreciates. Now I want you to notice something. When we did these right here, you see this was 1 plus, right? So if you kind of figured out what this was as a decimal, do you understand that this would be a number bigger than 1 right here? Okay? So when I raise a number bigger than 1 to a power, that's bigger than 1, and multiply by 15,000, that's going to be bigger than 15,000. Over here, notice that this right here is a number that's what? Less than 1. So remember when we grabbed the exponentials yesterday, we had that 1/3 to the x. What did 1/3 to the x do in terms of that graph? It decreased. My y values were getting smaller. Same thing here. So this card depreciates, right? So the value of the card should be doing what? Going smaller. And see, the base is less than 1. So it's going to be a decreasing function. Remember the graphs we did? Okay, so relate that to what we did in those two, in that lesson, part 1 and part 2. So it's going to decrease. That's why it depreciates, because this number is less than 1. So this was 1.806, then what should happen? Yeah, so my y value should be increasing. The value should be increasing. Okay? So relate that to the graph we did yesterday with exponentials. All right, and basically all you do is so it says determine the value of the car 5 years after you purchase it. So how do you do that? So how do you determine the value of the car 5 years from now? Huh? T is 5. So number two, so you're told that V of t is 18,000 times 0.806 raised to the t power, and I'm trying to find V of 5, right? Because that's what t is. Y'all agree? All right. So V of 5 would be, wherever you see the letter t, what do I plug in? 5. And it's just a matter of you using your calculator. So you just, if you what the calculator asks you to, then just typing it as you see it. So you're going to say 18,000 times 0.806 closed, and then raised to what power? A fifth. Now, do I need to put parentheses here? No, because it's just one number, right? So you can just say 5. If you want to put parentheses, you can, but I'm not. It's going to be 5. And so that's the value of the car. And what's the value? And now it says to the nearest dollar, not the nearest cent, the nearest dollar. So make sure you always follow directions. Read the directions. The nearest dollar. So the nearest dollar means the nearest whole number. Okay? Nearest dollar means the nearest whole number. No pennies, no change at all. Nearest whole number. So, but you got to look at the tens place. What do you notice about the tens place? It's 5 or bigger. So this becomes 6,000. Oh, wait. Okay. So 6,123. Okay. Now, I did also make this number up, by the way. I did make that number up. So, and remember, the depreciation depends on the car anyway, right? So, if you buy a Honda Civic, oh, do they? Okay. Oh, yeah, it does. Okay. But I did make that number up. That's possible. I don't know. Depends on the car. I don't know. Google it. See what happens. Dude, look at a blue book. The blue book. All right, 3. All right, so make sure you know what I mean by the nearest dollar. Make sure you know what I mean by the nearest cent. All right, 3, it says the population of a large city was 2.14 million people in 2005. The population can be modeled by the following function right here. Now I'm going to ask you this, without even, don't put in your calculator yet, is this population increasing or decreasing? It's increasing. How do you know it's increasing? Because the base is bigger than 1. Very good. Now on your worksheet, I made an error there on the worksheet I gave you, the part 3, number 3. You see where it has f of x and then the other variable's t? It should have been f of t. So just change the variable to a t. Because your variable is t on the worksheet. 4.1 part 3? Number 3, right? 4.1 part 3. Part 3. All right, but anyway, I gave that out last time, and I don't have any extra ones, guys. Number 3, it says f of x equal the something raised to the t power should be f of t. So your variables should match up. Okay, Now, I did go back and correct it on Canvas, so if you print it out, it'll be the correct one. But you can just go ahead and just write it as T. Okay, so now the question is, now this was in 2.14 million in what year? 2005, and they want to know what's the projected population in 2022, and then round nearest. I don't know why I said 100. I should have said the nearest person. Just go ahead and do that, nearest person. Oh, I know why I said the nearest 100th. I'm sorry. I can tell you now why. I'm sorry. Leave it like this. No, leave it like this. See the nearest 100th here? Right there. So that's why. Right here. Okay. When I thought of the nearest 100th, I meant like 5.67 people. But it's this right here. This is what I mean by the nearest 100th, okay? All right, so let's look at this. So leave it as 100. All right, so you get f of t equals 1.007 raised to the t power. Oops, 2.14. Okay. All right. Now, what's t in this case, do you think? How'd you get 17? There's no 17 in here. All right, so you said the year 2022 subtract 2005? Because in the problem it says that, remember the initial amount was 2.14, and that was the initial amount of what year? 2005. And so they're interested in 2022. Now, there's all kinds of variables that affects population change. So we're just assuming that this is going to be the same. That's going to increase 0.7% each year. So we're just making that assumption. What you said, 17? Mm-hmm. So you get f of 17 will equal 2.14 times 1.007 raised to the 17th power. All right, so let's see what we get. 2.14 times 1.007 raised to the 17th, raised to the 17th power equal, all right, so 2.41? Yeah. All right, now be careful, don't just say 2.41. That's not true, it's 2.41 million. Because at 2.14 was 2.14 million. So to answer, you need to put the word million. Okay, so don't forget the word million here. All right, so what I meant by the nearest 100th was this right here. Okay, 4. All right, so in a protected environment, the population P of a certain endangered species recovers over time, according to this model. So P of t equals 25 times 1.108 raised to the t power. And part A, it asks you, what was the size of the initial population? Based on our discussion, what do you think the size of the initial population is, or what? 25. 25, that number right here. That's, remember, your initial amount, 25. So there are 25, I don't know what kind of species this is, so I'll just say, let's just say 25. It could be animals, it could be plants, insects, I don't know. So just say 25. B, according to the model, what will be the population of species in 5 years? So in place of T, what do you plug in? All right, and just use your calculator. Now just let's see what you end up with. 25, 1.108 raised to the 5th power equal. So to nearest whole number, what is that? 42? Okay. All right, so that should help you with part 3 of that worksheet. Now remember though, you're definitely going to have a compound interest problem, so you need to make sure, and it says in the study guide, you need to make sure you can do Compound finitely and compound continuously. I'll give you the formulas for it. You have a formula sheet. Okay, so that takes care of part 3. Okay? Yeah, nearest whole number. Not round up, you round off to the nearest whole number. So this was 41.4 something, then would stay 41, right? Okay. All right. Okay, now let's look at 4.2 part 1. 4.2 part 1. Okay. All right, so section 4.2. All right, go ahead and take out 4.2, part 1. Where's 4.2? Yes, 4.2. Okay, so 4.2, you're dealing with exponentials and logarithms. So you're basically talking about the basic concepts of exponential and logarithms. In 4.2, you go a little bit more with it, and then in 4.4, you deal with equations, basically with more about equations. But in 4.2, we're going to talk about the basic concepts of exponentials and logarithms. All right, so make sure you look at the video on this because we're not going to talk a lot about what was on the video here in terms of the basic concepts, but there is a relationship between the exponential and logarithm. So if you have something like y equals b to the x, remember that's an exponential, right? Y equals b to the x. The exponent, a logarithm, is nothing but an exponent. A logarithm is an exponent. So I can write this exponential as a logarithm, and this is how it looks. So you have an equal sign because you have an equal sign here. So I'm going to rewrite this exponential function as a log function. And on this side, I'm going to write the word log for log. Log for log. A logarithm has a base. The base of a logarithm is the base of this exponential. What's the base of this exponential? B. So when you write the base of a logarithm, it's a subscript. It looks like this. That's how it looks. Okay? Now, the exponent of the exponential goes here. What's the exponent of this exponential? X. So X goes here. And this right here is going to be called the argument. Let's call that the argument. And the argument goes here. And the argument is going to be this y right here, what's on the other side of that base. Now you read this as this side right here, you read it as log of y base b. That's one way of reading it. Log of y base b. Or you can read it as log base b of y. All right, so what you're going to do in these two worksheets for this section, you're going to go from exponential to logarithm, and you're going to go from logarithm to exponential. All right, so, y is what? Y is,
The smallest, the B seems to be smallest, so why am I so big?
it's a, well, the B should be a subscript. I mean, it doesn't have to be smaller than the Y, it just has to be written as a subscript. Okay? So if you look at the worksheet, you see how it looks. Look at the worksheet. You see how it looks in the worksheet? So you just got to make sure it looks like a subscript. And they're really the same size, it's just that one's a subscript, one's an argument. All right, now notice how we went from an exponential to a logarithm. Remember, we said that a logarithm is an exponent, right? A logarithm is an exponent. So you see this x right here? You see how I'm saying this log is this x? Well, isn't that x this exponent? Okay, so a logarithm is an exponent. So whenever you're dealing with an exponential, remember an exponential, where's the variable located? In the exponent. So whenever you convert it back to to solve for the exponent, you're gonna rewrite it as a logarithm because that's what an exponent is. The exponent of an exponential is a log. All right, now how you're going to use this is not that difficult. Let's see, let me look at the worksheet. All right, so the first one, we're going to write each equation in its equivalent exponential form. All right, so write each equation in its equivalent exponential form. Number one, suppose we have 64 equals log base 4 of, make this 64, make this 3. 3 equals log of 64 base 4. Remember how to read this? 3 equals log of 64 base 4. Or you can say log what? Base 4 of 64. Okay. Now you want to write this logarithm as an exponential. All right, it's very easy to do. Remember, an exponential has a base, correct? Okay. So an exponential has a base. What's the base? The base of the exponential is the same as the base of the log. Base of the log is 4. So you have an equal sign, you have a 4 here. All right, now watch. Look at this. You take the base and you raise it to its exponent, right? So notice my finger. You're going from b to the x power, b to the x. See this? B to the x equals the argument. What's the argument? Y. So that's what you have here. So you're going to say 4 to the what? Third equals what? 64. Or you can say this right here. It doesn't matter. Okay? And that's all they want you to do, was to rewrite this as an exponential. All right, so all this is just making sure that you know this definition right here, how to go from one to the other in both situations. Okay, number 2, suppose you had log base 5 of x equals 6. Log base 5 of x equals 6. So you want to go from this log equation to an exponential. What are you going to write first? The base, which is what? 5. Then you write the exponent. What's the exponent? 6. Equals the argument. What's the argument? X. That's your answer. Log base 7 of 4 equals, let's say, y. I just made that variable up. It could be any variable. All right, you want to go from this log equation to an exponential. Okay, 4. You have the log base b of 16 equals 2. All right. So that's just going from logarithm to exponential. All right. So that's all you're doing. Use the definition. Okay. Now we're going to go from exponential to logarithm. Still using this definition up here. So write. Let me use another page. So we're going to write each equation in its equivalent logarithmic form. All right, number 1. All right, suppose we had 6 to the x equal 100. 6 to the x equal 100. So I have this exponential. I want to write it as a log. So you're going to put the equal sign, and you're going to write the word log. You're going to write the letters log. Okay, now what are you going to write next? The base. What's the base here? 6. Now you need to write as a subscript. So make this look like a subscript, like this. Okay, and then you put the exponent. Where does the exponent go? On the left side or right side? Left. So what goes here? X. It kind of makes sense because look, 6 to the what? 6 to the x, which is what I have here, equals the argument. And so you can say the log of what? Yeah, as you can say, log base b of 100 equal x. Doesn't matter. All right, then let's look at this. X to the 5th power equal 121. So equal log. What do I write first? Log of, and then what's next? What's the base? Subscript. Put the exponent next. 5, right? Now what's the argument? Okay, it's supposed to look like this. All right, 3. Let's say you had 9 to the x power equal 41. Okay, what's the base? What goes on the left side? What's the argument? All right. Okay, now let's look at this one. Suppose I had the 5th root of 22 equals, ooh, I made that up. I hope the one on the worksheet is correct. Okay, so see the one on the worksheet that has a cube root of 216? Yeah. Is that really 6? 6 cubed. What's 6 cubed? Yeah, that's correct. All right, so 216 is correct. So over here, I'm going to change this. Let's make this right here, because I don't want to take the 5th root of 22 because that's be a decimal. Let's say the 5th root of, let's put this at 3. So 3 to the 5th, 243. So it turns out that the 5th root of 243 is 3. Okay? All right, now I want you to change this to a log equation. All right, so I need the base, right? And what else do I need? The exponent. All right, now you could probably tell me what the base is. What do you think the base is? 243. So no issue there. The base is 243. And you could probably tell me what the argument is. 3. So again, no issue there. What's going to be the issue for you is determining what that exponent is. What do you mean the opposite of 5? The opposite of 5 is negative 5. No, I mean, I'm just telling you the opposite of 5 is negative 5. Is that what you... Now, you got to remember some things from last semester and the semester before that. What? No. Nope. Okay, you got to remember a couple of things from last semester, semester before. So, if you have the square root of x, last semester you learned that the square root of x, a radical, you can always write a radical with a rational, exponent, not 5. You can always write a radical as a rational exponent. So we x to some fraction. No, well, I'm talking about this now. Let's look at this. 1 over what? 2. So the square root of x is x to the 1/2. Because remember, what's that index right here? 2. So your index is your denominator. And x is being raised to what power right here? No. Right here, guys. 1. All right, so you say 1 over what? 2. So if you have the cube root of x squared, then that's x to what power? No. 2/3. Okay, 2 divided by 3. Your index is your denominator, your exponent is your numerator. The 5th root of x to the 4th power is x to what power? 4/5. Okay, so this right here is 243 to what power? 1/5. Now what is the exponent? 1/5. So your exponent is 1/5. So you had to remember some things about last semester. Actually, this is from Math 98. Okay? All right, so remember Math 98. You learned about rewriting radicals as rational exponents. Okay? All right, so that's how you do number 4 or number 5, whatever it is on your worksheet. Okay, now, so that part was just talking about going from exponential to logarithm to exponential, just using the definition. That's all that was. Okay, now let's talk about some properties. Let's look at this first. Without using a calculator, now on your test, you'll notice that on the study guide it mentions that there's about 4 problems that you're going to do without using a calculator. And here's the idea. What if I had the log, so simplify without using a calculator. Now, in one of the sections coming up, you won't be able to do what I'm doing without using a calculator. You're going to need a calculator. But in this section, these are simple enough using what we just talked about. You can do without using a calculator. For example, what do you think the log of 7 base 7 is equal to? So this is number 1. So I want you to find what is the log of 7 base 7 without using a calculator, using what we just talked about. 49. Okay. Anybody else? 1 is the answer. We just talked about the fact that a logarithm is an exponent, right? So a logarithm is an exponent. So I need to know what is this exponent equal to. So that number is your exponent. And so if you look at this, doesn't this equation right here, doesn't it kind of look like these? And when we wrote these, what did we change it to? An exponential. We changed it to an exponential. So when you do this, you're going to say, when you change an exponential, you're going to say the base, what's the base? 7 raised to the box equals the argument. What's the argument? 7. Well, if you look at this, 7 to what power is itself? 1. 7 to the first power is 7. So the answer is 1. 7 to the first power is 7. You're also going to learn that when you have an equation and the bases are the same, then what must be true about the exponents? They must be the same also. So this is a 1 right here, and this has to be a 1. Number 2, what if you had the log of 3? Log of 9 base 3. Log of 9 base 3. What do you think that is without using a calculator? Okay, y'all are not, and I'm going to say y'all, some of you, Amy in particular, is not using what we talked about. It's what? What'd y'all say? 2. a logarithm is an exponent. So the first thing you want to do is draw a box here. All right. Now rewrite this in exponential form. What's the base? 3 raised to the box, right? Equals what? So 3 what power is 9? 2. 3 squared is 9. So the answer is 2. It makes sense because 3 squared is what? 3 squared is what? 9. You don't even have to write this out because you have in your mind 3 squared equals what? 9. 7 to the first equals what? 7. 3 log of 1,000. Now there's no base. What is it understood to be? Oh, 10. Remember, your base can never be 1, right? Remember, we talked about that. The base of an exponential can never be 1. That was one of the statements we made. So the base of a logarithm can't also be 1 either. So the logarithm, if there's no base, it's understood to be a 10. Now, if you look at your calculator has 2 bases. One, see where it says log right here? If you press log of a number, that's assuming you're looking at what base? 10. All right. So remember now, the log without a base listed is understood to be a 10. So there's no base listed. It's understood to be 10. All right. So a log with base 10 is called a common logarithm. So your common logarithm is log with what base? 10. Common logarithm is a log with base 10. Okay, so tell me what you think this equals. What'd you say? 3. Because if you want to, you can write this as 10, right? I'm going to go ahead and rewrite it here. You agree that those two statements are the same? So equal box. So 10 to what power is 1,000? 3. 10 times 10 times 10 is what? 1,000. So 10 cubed is 1,000. All right, let's look at this one. All right, so remember, a common logarithm has what base? 10. So there's no base listed. It's understood to be 10, not 1, because your base can never be 1. You remember your base must be a positive number, but it can't be what positive number? 1. Okay, so let's look at this. Let's see. All right, so let's look at this one. Number 4. Log of 1.25. I keep saying log of. I meant log base 1.25 of 1. Now, I'll put 1.25 because it really doesn't matter what number is at base, as long as it's not a 1. The argument can be a 1, but the base cannot be a 1. So what do you think that equals? What do you think? Let's see if you remember something from last semester, and the semester before that, and the semester before that, because you did do that in Math 97. What do y'all think? Don't be shy. All right. 0. No, you guessed or you knew it? No, go ahead. Go ahead. Okay, so you remember in the last 3 semesters you talked about exponent 0. So 5 to the 0, 2 to the 0, 6 to the 0. What? Well, you need to know a lot from last semester and the semester before that. Remember, everything you learned in previous courses you need to know, right? It builds upon this stuff. So what do you remember about 5 to 0, 2 to 0, 6 to 0? They're all equal to 1. Any number raised to 0 power is 1. Any non-zero number raised to the 0 power is 1. So when you put this as a box, when you're trying to find out this exponent, you're saying 1.25 raised to what power is 1? 0. That's 0 here. Okay, number 5. All right, let's suppose we had log of 7, log base 7 of the square root of 7. Log base 7 of the square root of 7, or we can read it as log square root of 7 base 7. What do y'all think that's equal to? Square root of 7 is not 7. Square root of...
The square root is going to raise to the second power.
1/2 is the answer. Y'all already forgot what we talked about here. You already forgot all about this. I know. So when you write this as an exponential, you say 7 to what power is the square root of 7, right? What you want to do is rewrite this radical as a rational exponent. So 7 to the box equals 7 to what power? 1/2. So when the base is the same, these exponents have to be the same. So what is this equal to? 1/2. Number 6, suppose you had the log. Let's see. Okay, log base 7 of 7 to the 4th power. Log base 7 of 7 to the 4th power. What do you think that's equal to? Yeah. You see, you're not using what you just learned. It's 4. You keep doing the same thing, guys. Keep doing the same thing. Write this as an exponential because that's what a log is, an exponent. So say equals box. Okay, you're looking at this and you're saying, oh, the pot thickens, ain't it? Come on now. Write it out. Write it out. 7 to what power? 7 to what power is the argument? What's the argument? Okay, well, isn't that like we just did? So what's the answer? 4. Write it out. Don't start freaking out. You got to write it out. Use your knowledge. Okay, everything is there. Everything builds upon each other. All right, number 7. All right, now, let's kind of review something. Okay, so you remember that 3 to the negative second power is equal to what? No. No. Huh? 3 to 1/2? I know they're guessing. 1/9. 1/9. You got it. Remember, you rewrite negative exponents using what kind of exponents? Positive. Oh. B raised to a negative power. One of the things you learned last semester and semester before that was that whenever you have a negative exponent, you need to rewrite it as a positive exponent. And the rule said that if you have b to a negative a power, that's the same thing as 1 over b to the a. So this b to the negative a is located in the numerator. To make the exponent positive, you put it into the denominator. Then you also learned this. You also learned that if it's negative in the denominator, you put it in the numerator. So that's just b to what power? A. All right. So those are the rules that you learned I mean, it was 2 semesters ago, but you used it last semester at one point as well. Okay. Huh? I know. I understand. But y'all do see that there's a lot of prerequisites in this course, right? There's a lot of prerequisites, and you do understand that we can't cover everything y'all did last semester. Okay. All right. Okay. What? Oh, I know. And I'm reminding you. I'm giving you the most important things. Okay? And I'm reminding you. Okay. Okay, so let's look at this one. All right, let's suppose we had the log base, let's make this base 2 of 1 over 8. All right, that one's a little bit challenging. Okay, think about a lot of stuff you've learned in the past, although you probably forgot 90% of it. 99. All right, so what are you going to do first? Huh? Okay, so you're going to say equal box, and then you're going to write it as an exponential, correct? You're going to say, what's the base? 2. And 2 to the box equal what? 1/8. All right, so that's where we're at. What do you think the answer is? No. Not -4. Not -4. So one of the things you also did was -3 is the answer. One of the things you also did was you learned that you need to rewrite these with the same base. What do you remember about 8? 8 is what? 2 to the third. 8 is 2 to the third. So this becomes 2 to the box equal 1 over 2 to the third, right? Okay? And now what you want to do is, you see where this 2 is in the numerator and this 2 is in the denominator? You want to bring this to the numerator. So this becomes 2 to the box equal 2 to what power? No, I'm bringing 2 to the third to the numerator. Whenever you bring it to the numerator or the denominator, the sign changes. -3. All right? So if you have 1 over 3 to the 5th, listen up. Listen up. 1 over 3 to the 5th is 3 to what power? -5th. 1 over 4 to the -3rd is 4 to what power? -3rd. Oh, I'm sorry. You're right. No, you're right. I forgot. This is -3, so this is what? +3. Yeah. All right. So the sign of the exponent changes, right? Okay. So first thing you have to do was to notice this is base 2, so I'd like this to be base 2. Well, 8 is equal to 2 to what power? The third. Well, I'm trying to make it look like this, where the bases are the same, correct? This base is 2, but this base altogether is not a 2. It's 1 over 2 cubed. But I know from experience that 1 over 2 cubed is 2 to what power? -3rd. So now the bases are the same, so the exponents have to be what? The same. -3. -3. Yes. All right. Now, the next one is challenging also. Next one is challenging also. All right, number 8. Okay, suppose you have this. Suppose you have 6 raised to the log base 6 of 21. 6 raised to the log base 6 of 21. You're just guessing.
I'm waiting because I'm not even trying. Okay, so the base.
The base is 6.
Right.
All right. Okay, so, all right, so you see that the base here is 6 and the base here is 6. All right, so the base is the same, correct? Okay, so whenever this base and this base are the same, the answer is just the argument. And so the argument would be what? 21. All right, let's think about this. Let's assume it is 21, okay? All right, so I have this exponential, correct? Okay, so we're saying, I was going to write it as a log equation, so, as exponential, so 6 to the 21st equals the exponent. What's the exponent? Log 6 of 21? So that's not going to help you there to see why it's 21. Okay. No, it's not. Well, don't. It's not that idea. No. Let's go. Okay, let's go back to the definition. I think it'll work out if we go back to the definition. So remember the definition we had earlier was y equal b to the x, and then x was log base b of y. All right. So right here, I am going to rewrite this x with this. You see this right here? Okay, so I get y equal b, and what's x equal to? All right, now notice right here. See this right here looks like this, right? Okay, so whenever this base and this base are the same, then what's that equal to? Which is the what? The argument. So that's the best explanation I can give you for that. All right, so that goes back to the definition. There you go. So remember, using our definitions earlier, a log is a what? Exponent. So this x, in place of x, I'm going to plug in this right here. All right? Now I'm covering this up. This looks like this. Well, we know that b to this is equal to y, right? Well, that y is the same as what? The argument. So whenever you have these bases the same and the log is in the exponent, then the answer is just the argument based on this idea here. So if you have 8 raised to the log base 8 of 2, then the answer is just what? 2. Answer is just 2. When the numbers are different, you have to use a calculator. So if the numbers are different, if the bases are different, that's a calculator problem. So remember, this is do these without using a calculator. Okay. Yes. We haven't done that yet. Yeah. It's going to be in a worksheet coming up. Yeah. So it's not in these two sections. No, it's going to be in section 4. I think it's 4.3. Yes. Not yet. No. Okay. All right. Now, the next, so that's worksheet 1. You can do worksheet 1 with this. Okay, worksheet 2. Who has worksheet 2? That was all for 1. Worksheet 2.